you should hear a message. All right. Welcome everybody to this Luceda Academy webinar about Aluminium Oxide, a new material platform for integrated photonic applications. Today we have some very nice speakers. We have Sonia with us, Sonia Garcia Blanco. She's a full professor at the University of Twente and co-founder of Aluvia. We have Jonathan Hong with us, who is professor at ETH Zurich. And we have Matt, who is application engineer at Luceda Photonics. The program today looks like this. We are going to start with the introduction, and then Sonia will first talk about Aluvia. Jonathan will go through PICS for ion traps, and Matt is going to show you how to set up a photonic design flow with the Aluvia PDK. So we start with Sonia. So Sonia, after obtaining her master and PhD degrees and carrying out research in many universities around the world, she joined the University of Twente in 2010, where she is currently leading the Integrated Optical Systems Group. She's focused on developing novel materials and integration technologies for integrated photonics. As I mentioned before, she's the co-founder and CEO of Aluvia Photonics, which she will now introduce in her talk titled Aluminium Oxide Integrated Photonics Platform. Go ahead, Sonia, the stage is yours.
Yes, thank you very much, Chiara, for organizing the webinar and also for the nice introduction. And I'm gonna try to share my screen. Let's see if it works. Okay, can you see my screen?
Almost, I think it's on me. Yeah, I can see it.
Okay, and I'm using my pointer as well.
Yeah.
Okay, now you see my screen and my pointer?
I see your screen.
Everything looks great.
Okay, perfect. So yes, so I would like to introduce Aluvia Photonics as a photonic integrated platform for applications in ultraviolet wavelength range. So I will introduce first Aluvia Photonics, and then I would like to give you a little bit of more details about what the Aluminium Oxide platform can do at different wavelength ranges. I said, okay, Aluvia is focused on UV, but the platform can also operate in other wavelength ranges. I can show here around 1 micrometer in the C-band and at 2 micrometers. And then I will conclude the presentation. So let's start. And probably you have all heard about the quantum advantage and how interesting quantum computing could be in the future. And then you also have heard that to do quantum computing, you need qubits. And then probably you have seen as well that to make a qubit, you need a lot of, a big setup. And these photos are taken in the Professor Holmes' lab, who will be giving the second presentation. And you can see the kind of complexity to be able to operate these systems, no? So you need a lot of light sources, UV, V's, and near infrared. You need some optics for light conditioning and some optics for light delivery. So if you want to do a useful demonstration with hundreds or even thousands of qubits, you will need to be able to pass from a complex system like the ones you saw before or this one into a little chip that you can fabricate on the wafer. And you can achieve that by photonic integration. Thanks to photonic integration, as you probably all know, you can gain energy efficiency, increase speed, reduce size, cost. You can implement novel functionalities, and very importantly, you can get scalability. And there is a couple of extra requirements which are quite specific also for quantum applications, is that you need operation from ultraviolet till the near infrared, and we will learn more about this in the next presentation. And also you need ultra low losses. If you look at the commercial platforms, commercial photonic integration platforms in phosphide, silicon, silicon nitride, you see that they operate above the visible wavelength range. And they are now enabling many applications that are already commercially available. However, when you look below 400 nanometers, you realize that, yeah, there is a lack of a commercial platform. Where do you get the peaks? And the Aluminium Oxide platform has a very broad bandgap and therefore can operate from around 200 nanometers till the near infrared in the same platform. So that has quite a lot of advantages, and that's how we decided, oh, let's offer this platform commercially. And last November, we started Aluvia Photonics. Here are some photos illustrating the performance of the technology. You see here in this photo on the top left, a propagation of a slab mode at 377 nanometers of wavelength, and the propagation losses are around 0.5 dB per centimeter. In the bottom left picture, you see a spiral operating at 369 nanometers with around 2.3 dB per centimeter of propagation losses. In the photo on the middle bottom, you see a UV tunable laser operating around 400 nanometers, which is a collaboration between the University of Twente, Aluvia, and another group here, and PHIX. And on the right, you see an amplifier, because we have topped the aluminium oxide with erbium, and then we can get amplification in the C-band, as I will discuss later. And we demonstrated more than 30 dBs of gain, and the passive losses are around 5 to 10 dBs per meter at 1550. So yeah, those are kind of interesting results, and therefore we can offer the technology now commercially, and that is what Aluvia Photonics is set up to do. So we offer foundry services of photonic integrated circuits in the aluminium oxide platform to enable markets for broadband operations, so from the ultraviolet, like these ones here, to the C-band or even 2 micrometers. And we hope that thanks to having the availability of these peaks, we can enable new markets, such as structured UV microscopy, UV Raman spectroscopy, UV-Vis spectroscopy, wildlife sources, tunable lasers, AR light engines, and the subject of the second presentation, quantum ion traps. We do the manufacturing here in Twente, in the Mesa Plus Nano Lab, where we have all the capability to go through the whole process flow required to fabricate these peaks. So let's go a little bit more details about the capabilities of the platform, and we can start with the operation in the ultraviolet. So we wanted to find out how low we can go with these layers. So we did an experiment in which we deposit a thick layer of aluminium oxide on a quartz substrate, and we used the quartz substrate also as reference branch, and we did UV-Vis spectroscopy, and we observed that the transmission is uniform until around 220 or so nanometers. And we are now analyzing a bit better even this transmission based on ellipsometer measurements. And we see that, yes, the band gap is here around 170, 180 nanometers. Here is a measurement, as I showed before, of the metricon. So it's a slab propagation at 377 nanometers. And we're measuring as deposit layer 0.5 dB per centimeter. And this was for a 70 nanometers thick layer. After the layer, we structure it and we make channel waveguides, and we do spirals with different lengths to do the cutback method. And with this method, we measure the propagation losses at 405 nanometers and 369 nanometers of wavelengths, and we achieve around 1.5 dB per centimeter at 405 and 2.3 at 369. This is for a cross-section around 70 nanometers thick and 600 nanometers wide. And then you can do devices. In this case, it's a demonstration of an external cavity tunable laser. So we have the peak where with the vernier ring and the phase shifters to tune the wavelength. We have the game material, we have it integrated and then packaged by PHIX. Okay, that was ultraviolet operation, and then we can dope the material with different rare earth ions, and we do that by a reactive co-spattering. So we have the two targets, and we deposit simultaneously the aluminium and the ytterbium, erbium, or thulium doping. So the ytterbium emits at around 1 micrometer. So we made a ring, we pump it, and then we see that actually it lases. And this was a very rough demonstration. And we achieved from this ring around 250 kilohertz free running line width with a 1.6 milliwatt of on-chip threshold. The efficiency was pretty low, but yeah, that was the first demonstration that we did. But that shows that we can have operation and even amplification at 1 micrometer. We doped it with erbium to do amplification in the C-band. So the first thing we wanted to know were the passive losses at this wavelength. So we designed some rings and we measured the internal Q as a function of wavelength. So we can see here, we use the tunable laser to characterize these rings from 1500 nanometers to 1600 nanometers. And the Q ranges from around 4 to around 8 million. So then from there, we extracted the propagation loss in dBs per meter, and that range as a function of wavelength between 8 dBs per meter all the way to around 3-point-something dBs per meter. We integrated then the doped material, so we doped with erbium, and we can have two ways of making the devices. In this picture in the left, the whole device is in aluminium oxide, so it's basically just an amplifier from the beginning till the end. And in the picture here in the middle is a combination of our material in aluminium oxide with silicon nitride, which is passive. So you couple to the silicon nitride, and then with some adiabatic couplers like the ones I show here in the picture on the right, you can go with low loss to the aluminium oxide, doped with erbium, you have the amplifier, and then you come back into the silicon nitride, also adiabatically. We characterized amplifiers, so we did again different devices with different lengths. Here you can see the cross-section and the mode. And here in this graph on the right, we can see the internal net gain as a function of launched signal power for a pump power of 130 milliwatts. And the doping concentration of erbium is around 3.9 10 to the 20 ions per centimeter cubic. And you can see here the gain for two wavelengths at 1532 at 1550. So at 1532, we can see that we have over 30 dBs over quite a large range of launch signal powers. And at 1550 is around 15 dBs. Finally, we dope it also with thulium for operation at 2 micrometer. And this was a paper, a work in a European project in collaboration with other partners in Femtochip, with a group of Nitesh Singh. And here we have a silicon nitride waveguide, and we deposit just like a layer of aluminium oxide doped with thulium, and that produces a very large mode amplifier. And here is the device. And you can see here the doped region where the gain happens. So they made this design of the cavity, and they achieved over 200 milliwatts of output power from this device with a slope efficiency of over 40%. So to conclude, the aluminium oxide platform provides low-loss broadband operation from the UV around 200 nanometers to the mid-infrared. We can dope it with rare earth ions, and then we can obtain amplification in different wavelength ranges. And now these peaks are commercially available via Aluvia Photonics. And the reason for this webinar, we have recently partnered with Luceda Photonics to develop the first Aluvia PDK. And the Aluvia PDK can be now obtained soon, in the coming days, via the Luceda website. And we're planning two MPWs. The first one will be at the beginning of October for a thick layer aluminium oxide for near-infrared applications. And the second the third MPW will be at the end of October for the UV applications. And we will get the exact data released next week in the design manual. And if you want to participate in these MPWs, please register via the Aluvia website. So that leads to the end of my presentation.
Very nice. Thank you so much, Sonia. Thank you for your presentation. We have some time for questions. Please feel free to unmute yourself if you want to ask any questions. You can also write your questions in the chat if you prefer, and then I'm happy to read them out for you. See, a couple of people have the hand raised. Maybe you have a question. Feel free to unmute and ask.
Well, thank you very much for. So the equation you showed in the slide that you can make equation of here
I'm sorry, Evgeny, we cannot hear you very well. I would suggest maybe you can write the question in the chat and then I can read it out for you, if that's all right. In the meantime, we have a question in the chat from Michael Kissner. Thank you, Sonia. Will the erbium doped version be available in the MPW?
We're working on that, not in the first two MPWs, but we will introduce it in the MPW, yeah, in the coming months.
Perfect. I see, Kantan, you have your hand raised. You can go ahead if you want.
Yeah, thanks, Sonia, too. It's a very nice presentation. So I want to know, yeah, you know, the loss is already pretty low now, right? So how much do you think you can still push the loss to be, and what's the current loss mechanism for now? Like, will you further improve the cell wall roughness or absorption, right? Well, thanks.
Yeah. At the moment, the losses are limited by the roughness, by the sidewall roughness. So we will be working on that in the coming months. So every run hopefully will have better propagation losses. So these are the ones that we have at the moment. So we're working on that.
Thank you. Another question. How do you couple light to photonic integrated circuits in UV? Do you have gratings?
So at the moment we have edge couplers and we do bad coupling.
All right. Another question is, does integration with silicon nitride, was it done by flip chip bonding, or can silicon nitride be grown in the same reactor?
So what we did was monolithic integration. So the silicon nitride is done by LPCVD, and then we deposit our aluminium oxide by spattering on top.
All right. There's a follow-up question to the previous one about the edge coupler. The question is, what is the edge coupler loss?
Yeah, that we have not, how you say, systematically characterized, but I believe in the last measurements for the losses at 369 nanometers, I'm going to give a number, but please take it with a pinch of salt because I can verify it later, was around 5 dBs, I believe.
All right.
I have a quick question as well, if there's time.
Sure, go on.
Yeah, very interesting talk, thank you. I know one of the problems with erbium is if you have too high concentration, you get self-quenching between the erbium ions. Is that something you've explored in different concentration runs? And do you think there's scope to push the gain per unit length there or not?
Yeah, we're actually working on that. We have seen that for the concentrations that are presented here was 3.9 10 to the 20 ions per centimeter cubic. There was no quenching, but that was the highest concentration we deposited so far. So not that it's not possible, but we need to do more runs and increase it and see where is the limit.
Cool, thanks.
It's work in progress.
We have a couple more questions. One is, could you expect implementation for mid-IR wavelength?
At the moment, we are not working on that. We're working at 2 micrometers. But of course, that will require a thicker aluminium oxide. And yes, yeah, I think at the moment, without any modification to the platform, we could go up to 3 micrometers because the SiO2, the limitation of the absorption of the SiO2 in the glass. But yeah, past that, more development will need to be done.
If I remember correctly, you were working on a funded project for mid-IR?
Yeah, we were working in the femtochip project and we're working with thulium. So we want to do devices operating at 2 micrometers.
Perfect. Last question. Did you consider using grating couplers for coupling?
It's possible, yes.
So is there something you might offer later on in your PDK?
If there is demand for that, yes,
okay.
Of course.
All right. So if you have a need for that, make sure to let Sonia know. Thank you everybody for your questions, and thank you, Sonia, for the nice presentation.
Thank you.
Our next speaker is Jonathan. So Jonathan, after obtaining his master and PhD degrees and working at various universities in the UK and in the US, he joined ETH Zurich in 2010, and he was appointed full professor in 2019. His research focus is investigation of quantum state engineering, simulation, and information processing with trapped atomic ions. And today he will present about photonic integrated circuits for ion traps. Go ahead, Jonathan.
Okay, thanks very much. I hope you can see my screen. Zoom tells me you can, so I'm going to be assured that that's the case.
Yeah, I can see it.
Good, thanks. Okay, so I show a plot here, which I often use for introductions to what quantum computing is. And sorry to start with a graph. I'm a physics professor, so I somehow have to do that. But what you see along the bottom axis is somehow an incrementally increasing size of problem. You can think of that as a linear increase. And what I'm showing on this graph is really the scaling of the runtime of a certain set of problems, which goes up exponentially when you have that on classical hardware. So all the computers you know today work with classical hardware, and this exponential scaling for these various problems is very problematic because quickly you get to a size of problem which you cannot do. And the promise of quantum computing, when it's been promised since sort of 95, I think people invented the first algorithms, is that the scaling is very different. And you can see that in this yellow curve, though I give a clock speed, which is much slower for the quantum computing. At a certain size of problem, it's massively outperforming the classical computer. So really the message from this is that to be able to have effective quantum computers, you need to build them big enough to cope with certain sizes of problems. Yeah. So the problem is not in building very small devices, but is making big enough devices and scaling them up and having higher quality enough that they can outperform these classical computers. And what sort of problems could they solve? I think the most important class that I can think of are chemistry problems. Here you're sort of seeing a cartoon of how we do fixation of nitrogen from the air, right? And we do it in these highly industrialized, high pressure, high temperature processes. But at the heart of what nature uses to do the same processes are certain molecules. And we have trouble understanding the reaction chains in these molecules. And so you can go to my colleague, Marcus Soraya here at ETH and ask, where would be an interesting place to start for doing these molecules? And you need basically 1,000 perfect quantum bits on a quantum computer. And he would say that would be amazing. I can go and do lots and lots of different molecules. I'd have a lot of fun with this device. But the problem is that when we build them in the lab, they're faulty. And so in fact, what this means is that we have to put about 1 million quantum bits as we would build them in the lab into such a quantum computer. And this is then the target, what we're looking at trying to build in order to build effective quantum computers that are of use to my colleague, for instance, in chemistry, and would be hopefully of use to making industrial processes more efficient. So where are we today? The approach I work with is based on these single atoms. So actually what you're seeing in this photo is a picture of 110 calcium atoms trapped in one of the ion traps that we have at ETH. And we control these atoms. They get trapped by electric fields, but we control them with laser fields. So you can see this mock-up here where I'm imagining that I'm shining a laser on 2 of the atoms, and that's allowing you to perform operations on these. And we can get to some 100 and so atoms, but that's very far from the 1 million I just told you about, for one thing, right? But also as this thing gets longer and longer, it becomes an intrinsically complicated system to deal with. So one of the approaches to scale then is to break these chains up into smaller chains and go for a more modular system. And here, an example below is actually a representation of a trap that's in a company called Quantinuum. I think I would say this is the leading quantum computer you can use today on the cloud. And basically, they have about 32 qubits, right? They have what I would say is excellent quality of operations, but they have, this is all done in this particular chip. And you can see that actually what's happening here is that there is a bunch of laser beams that come to 4 spots, and there are only 4 spots where they control atoms, and each of them is directed then pairs of laser beams which cross the individual spots. So even in this very simple device, they only use 4 of these regions. then they have a mess of light going all over their chip, right? Because they do everything in free space. And so fundamentally, you can look at this and you can see that this is just not scalable to numbers of 1 million. And you can ask, how do I make it scalable? And of course, the answer in the context of the talk today is you do that through integrated optics. You take the chips that we use to trap the ions, you integrate optics into them, and you deliver light directly from the traps to your atoms. So this is sort of the cartoon of where we'd like to go, right? We would like a chip which anywhere above these sort of racetrack structures can trap individual atoms, but wherever we need light, we can just direct it out of the chip, and maybe 50 microns above the chip surface, the light travels and is focused on some individual atoms, and that's how we do the computation. And how we think of it in the lab is, for instance, we have to have a laser to seed this system. We need some sort of fiber or waveguide distribution network to take these different paths of control through different systems of modulation. And then we feed that into some sort of vacuum system, actually a cryogenic vacuum system, where is our integrated photonics chip. And this was all something that was a pipe dream until sort of 2018 or so, and MIT did some pioneering work, and we've followed up on that. And here you see one of the first chips that we've used. This was a chip where you see here a fiber bundle of 8 fibers coming into this chip structure here. You see actually on the top the gold electrodes, and the ions are trapped 50 microns above this chip. Now, what was going on in this chip is actually that we had integration of lots of wavelengths, and you see the wavelengths here, they're in the visible and IR, and they're all integrated in a silicon nitride platform. The silicon nitride chips were made by Linux International, and then we operated these chips. We dealt with the on-chip coupling with a similar butt coupling to what I think Sonia described earlier. And the nice thing was that in operating them in our initial results, we were able to do high fidelity operations, which is kind of the crucial operation for performing quantum computing in these sort of in this architecture, if you like. And more recently, in the last months, actually, we've started to get multi-zone operations up and running. And it's very nice to see that the students really just plug in fibers to 2 different fibers and they run multiple zones. And just to compare that, the Honeywell chip that I showed you before running 4 zones is a system where it's maintained by an entire company. These are 100 people or so that's running this system. Yeah. So this is very encouraging, but it's not the end of the story. We have to scale this up further. And first steps in scaling are to think, how can you network whole arrays of traps? So here is our next generation, and you see in this generation that everywhere there's a white dot here, the white dot is the fake bit, is where we plan to have an ion trap in this system. So there will be 20 ion traps on this single chip now, which is something that's totally unthinkable with free space to my mind. Yeah. You also see the wiring, and you see wiring, which is optical wiring here, which is coming in either at silicon nitride for the wavelengths I told you about before, but actually critically is also in alumina to bring in ultraviolet wavelengths. And just zooming in on one of these zones, then you see there's an additional coupler here that I didn't have before, which is for 397 nanometers. And that's because in the calcium ions that we use, we need these ultraviolet wavelengths for some of the transitions. Yeah. So in the previous chips, we were limited. We ran them all with 729, 854, 866 integrated, but we still had free space beams for doing the 397. And in this new generation, we expect, with the help of Illumina, to be able to just use integrated optics. I should say that there's a bunch of design work going in there, especially on the grating design. There's a recent paper out that we have on how to do delivery of light into focused beams from the integrated optics into cultured beams, if you like, for our ions to use. So with that in hand, I just actually moved from the integrated optics layer, and now you see that the process has actually been finalized for also the electrodes. And here you're looking down, you can kind of see a little bit of the profile of the electrodes because of the surface, or some sort of surface roughness, if you like. And you see in particular all the little holes in the surface, which are for letting the light through. Yeah, so there's a gold surface on the top here. So I think the take-home message of that is that even in calcium, which is probably the most friendly ion for integrated optics, maybe barium would rival it, there's a need for near UV and UV wavelengths to be delivered from these chips. And in particular, we're looking to get reasonable powers through 10 to 100 milliwatts, and we need extremely stable performance. And in that, we need materials that will sustain that. And we think from seeing the results recently, we think that Illumina is probably a very good candidate for that. And that's why we sort of are interested and are actually collaborating with Sonia on developing these sort of chips. So with that, then, I think that's the most of the science. I just remind you of the challenge of where we're going is towards trying to do 1 million, not 10 or 20. But that's very seriously going to rest on being able to do integrated optics. And I think we're going to have to look at a variety of materials. I haven't told you today about modulation and the challenges of doing that. And again, that's going to lead us into a range of different materials, I think. And it's an ongoing and a beginning challenge for us to deal with. So thanks for your attention, and I look forward to any questions.
Thank you so much, Jonathan. Like before, you can feel free to unmute yourself to ask any questions, or you can write them in the chat, and I'm happy to read them out loud. All right, we have our first question. Why do you prefer to use calcium instead of other type of ions?
Okay, that's a good question. I think there are many ions that we have. In fact, in my group, we also use beryllium ions. So somehow one thing is about the mass of the ions. Beryllium is the lightest. Calcium is sort of the third lightest we could use. But if we want to do integrated optics, previously, then beryllium was out of the question because the wavelengths are all around 313 nanometers. And so calcium was very favorable for a start into integrated optics. I think if you come from the integrated optics angle, then the easiest two are probably calcium and barium. Barium has even longer wavelengths actually than calcium, but barium's very heavy. And for us, sometimes we like that the ions vibrate quickly. And for that, it's better to have a light ion than a heavy one.
All right, thank you. The next question is, how are the ions trapped above the photonic integrated circuits?
Yeah, so that refers to the fact that we've got gold layers on the top, and these ions are charged, they're charged particles. So we can apply electric fields to these surfaces. And actually, there's two ways that we're doing this now in my lab. One, which is sort of probably the standard approach, is to actually apply radio frequency voltages to the surfaces, and that allows you to trap the ions, which has the problem that all these chips have to have high voltage radio frequencies on them. Mm. And the other, which we've moved to very recently and have brand new experiments on, is just to put the system in a big magnetic field. And then what that means is we can get rid of the radio frequencies. And we think that might be much more scalable. But it's less mature, so we're still working on that approach.
The next question is, why do we need 397 nanometer laser?
Okay, so every atom basically has a set of energy levels, and these tell you which frequencies of lasers you'd like to use. And 397 is the sort of first laser you would think to use in calcium, because it's the one you use to cool the ions down initially. Recently, we found ways of evading using 397, but there we then have to use very high intensity of light. And so it probably is favorable to have 397 there because it's basically our cooling light. It cools the ions down. It is also, when you see a picture of an atom, you're actually seeing 397 nanometer light from calcium atoms because that's what they scatter.
How do you modulate the light on chip or off chip, and how fast do you need?
That's a very good question. I think so modulation, we use it for different reasons. So we use it to tune the frequency of the light, but we also use it for switching beams on and off. So we're using acousto-optic modulators typically. And there, I think the timescales are not particularly challenging. They're sort of on the level of 1 microsecond. We could probably go even a little bit slower. The pulses are typically a few microseconds to 10 microseconds long. We don't necessarily need the frequency shifts. We can sort of precondition light to be at the right frequency. But one thing to point out, which I think is more challenging, is the stability of the light that we're delivering to the ions has to be very high to perform good, high-quality operations. So we look to get to intensities which are on the level of a part in 1,000 stability for these pulse sort of shape areas, I would say. And so if it's a modulator that then drifts in how much light it lets through or has interferometric stability, we would worry that that's not stable enough in the power that it can deliver. So that's probably the bigger challenge for the modulation.
Perfect. Okay, very last question. It just came in. When you mention you need high power, 10 to 100 milliwatt, is it the power needed to address one single ion?
Mm-hmm. I think that'll depend. So we're in the latest generation of grating couplers, then we're starting to think that we can focus to very tight laser spots where the ions are. And then the power that we need, the power need comes down because we can get high intensity. And what we care about is intensity. The ion is essentially a point particle. Yeah. So in that sense, then what do we need? I think certainly there will need to be hundreds of milliwatts going into any chip that delivers light to many zones. Because you just have 20 zones, you're going to divide the power by the 100 by a factor of 20 down to 5. I'm sure we'll need 5 milliwatts per pair of ions or so to be doing gates at a reasonable speed.
All right. Thank you, Jonathan, again for your presentation.
Maybe I just answer the last question.
All right.
Yeah. It says, at what temperature does the quantum computer operate? If at cryogenic temperatures, how does this affect the integrated optics? Can this be taken into account? So we've been operating at 4 Kelvin. For the integrated optics, we found a way of bonding fibers onto the chips that was basically giving us a 1.5 dB loss at room temperature or at 4 Kelvin. So in that sense, we don't see a huge difference in working at 4 Kelvin or at room temperature. We get a huge win because we don't have to worry about materials when we go cryogenic compared to being at ultra high vacuum at room temperature.
Perfect. Thank you so much for the presentation and the nice answers, and for everybody who asked questions. That we can now switch to our third presentation and last presentation from Matt. Matthew completed his PhD in physics at the Optoelectronic Research Center at Southampton University in 2020, where he carried out research work about free space optical experiment design, photonic simulation, and integrated circuit design. Since January 2023, he has joined the Luceda team as application engineer, and today he will present to you about photonics design flow from a software perspective and the Aluvia PDK.
Hi, I just want to say again, thanks for a wonderful talk. It's always really interesting to see like the direction that the fields are going in. I'm coming at this from a slightly different angle now. I'll be talking about how you can use software integrated into your design flows and what are the tools you need to really enable some of these more advanced features. I'll start with a quick introduction for Luceda Photonics. We're a Belgium-based company. We were founded in 2014, so we're coming up to about 10 years now. But we do have a much more global presence than 10 years ago, with resellers and teams across the world. Our ethos has always been this first time right experience. And what we mean by that is in electronic design, you simulate a circuit, you design it, and you click go, and you know it's going to work pretty much every time. And that's a level of maturity that we still aspire to in photonics, and that's something that we really strive for in our products. What does that mean? It means reducing the design errors. It means sort of standard languages that you can take between different foundries or different teams, and that everyone is sort of working together using the same standard tools. And the other benefit as well in the bottom corner is to improve the time to market. Currently for photonics, it's very long lead time, 6, 9, 12 months between sort of design and testing, which really slows down innovation. What is IPKISS? IPKISS is the main product of Luceda. It's a Python-powered design library that we use for photonic chips. It's fully parametric, and really that's kind of going to be the core of what I'll show at the end. And it's well integrated with lots of different PDKs, including now Aluvia, as well as third-party simulation tools. What do I mean by circuit design? Obviously, the main output people usually think of is a GDS file that you send out, but we also support much more than that, including sort of circuit level simulations using our internal tool Caffe. The nice thing about doing it this way is that you can really link your simulation and your design all in one flow. So you don't have to build a simulation, extract the results, and then separately build a chip and hope that you haven't had any translation errors. And as I mentioned, obviously we have full GDS exports and some post-validation layout, net list extraction, some nice features. And then the kind of final pillar for our software is the PDKs we support. We obviously here to talk about Aluvia, but also you might need packaging for your chips as well, or you might need to co-package with another technology. So it's always nice to have a large range of technologies to choose from. And it's done in a way that you can take an existing design and very easily move into a new material like alumina with very little headache. We also have a lot of training and support. So most of my job is helping customers, teaching them or solving problems together. We also have online resources, and we offer a lot of events like the one you're at today. The other thing we have is also services. We offer services for sort of building PDKs and more specialist things, but I won't talk about that so much today. So what does our platform look like? Well, as I mentioned, we have the PDKs with different materials: silicon, indium phosphide, silicon nitride, alumina. We have packaging. Then we have the sort of core engine IPKISS, which is where you take the tools that the PDKs offer and the technologies and build your designs, or sort of do component fabrication or component simulation and design. And then we also have some modules that go on top of that, things like the AWG designer for designing AWGs, and the IP manager, as well as the third-party links I mentioned. We really like to see sort of the whole photonic ecosystem flourish, and I think a good way to get that across is like these are all the ecosystem partners we have, and we're always looking to add more. So I mentioned PDKs quite a lot. In case anyone's not too familiar, just a quick recap of what a process design kit is. In my mind, it's two separate but related things. The first is an underlying technology. So if you're working in aluminum oxide, which layers do you have access to? Are there metal layers? How thick are they? All of these things. What are your minimum fabrication tolerances? All these things that are defined sort of often at a foundry level, but need to be carried all the way through to a design. And then the second part is often a standard library of components. So if a foundry has done the hard work for you and simulated and tested and verified all the common sort of toolbox components, then that's wonderful. It saves you a lot of time, and it really de-risks any designs you have. And the benefits to this approach, which is we ported over from electronics into photonics, is that it massively improves the time that it takes to design a chip and makes them more reliable, as well as it brings a much closer level of integration from an idea in your head all the way through to a final chip. There's different stages, and at each point you can sort of test against what you expect to happen and what you're told will happen. What does this look like? Obviously, a foundry has to come at some level from a PDK has to come from some level from a foundry. They're the people in charge of the process and always innovating and improving. And there's the two sort of branches I mentioned with the technology and the component library. How this might be used in the real world is that from this PDK, you could create a library of internal components at your company or your research center. And from those components, maybe you've assembled multiple smaller PDK components into a subcircuit, and then from there you can build up all the way into a new design. And obviously this is a very sort of scalable approach. You can have multiple different designs or different libraries depending on the different technology platforms, all sort of working alongside each other without any sort of integration problems. The next thing I wanted to talk about was the Aluvia PDK itself. I think it's always being added to. This is maybe not extensive, unfortunately, but currently there's all the basic blocks that you would expect to see. We've got some MMIs and Y splitters. There's directional couplers, ring resonators, spirals, etc. And it's all parametric. So something you'll see later is these aren't fixed components. If you want to design a ring resonator for a very specific wavelength, then all you have to do is pass in the length you need into that ring, and it's done. And as we'll see in 2 slides time, it really speeds up the process. The first thing I did when I was playing around with their PDK is to build this splitter tree. It's something you may have seen in our other training material or online. It's something we really like because it shows the power of IPKISS. And in this case, these are the optimized 1x2 MMIs from the Aluvia PDK. And I've written about 40 lines of code, which I can now pass. I can call this with any number of splitter tree levels. So this is a 5-level tree with 1, 2, 3, 4, 5. I don't know how many outputs they've given me off the top of my head. 2 to the power 5 to the power, no, 2 to the power 5. But you can see how you can really create these reusable toolkits that if you're making an OPA, an optical phase array, and you need 128 lanes or something, it's very easy to split the light. And something I was thinking is when Jonathan was showing earlier, the laser coming onto the chip and then being distributed, this is exactly the kind of structure that could help with some of that. And then the last thing for me today is I just want to talk a little about hierarchical design. And what that looks like using a PDK. What I mean by this is that you can take small building blocks and assemble them together into more useful bits and just plug and play. So as we mentioned, you could build your own library. What I did over the course of about an hour and a half yesterday is I built a small grating coupler, and then I took the ring resonator from the Aluvia PDK and coupled that with a spiral. So this could be used as an on-chip amplifier, which I think is actually exactly what Sonia was showing earlier, pretty much. Or a very similar application would be for biosensing if you could open a window above these. But then you can, you have your sort of amplifier here as a single unit, which you can then array in multiple ways. And then finally, you can do all the routing. In this case, I've just done some slightly odd bundle routing to the top and bottom of the chip just to be different. But I just wanted to give you a flavor of what's possible and how easy it is. This design start to finish, including custom gratings, was about an hour. And it's all because of the components that I don't have to design my own spirals, which if anyone has tried that before, they'll know it's a bit of a headache. So yeah, that's all from me, nice and quick. But if anyone has any questions, then just ask. And thanks for listening.
Thank you so much, Matt, for the nice presentation. We can leave the floor open for questions. You can feel free to ask questions to any of the speakers if you have questions for Matt. That's, of course, the right time to ask, but Sonia and Jonathan are also still here, so feel free to ask.
I didn't think there'd be so many. It's slightly less interesting than the ion trapping and on-chip lasing, sadly. Is the grating coupler in the library?
Yeah.
No, that's something I just added earlier. It's optimized for 1550, so I will not be sharing that with anyone here. You'll have to have a look yourself, I'm afraid.
Maybe if you are interested in designing a grating coupler using the Aluvia PDK and you're a Luceda customer, you can feel free to send the question to our support channel, and then we are happy to support you doing that. Or we can also take it up with Sonia and align with her and make sure that we can add a grating coupler in the PDK. Okay. I'm going to leave like a couple of seconds more for questions. We have one from Pierre. What is the minimum band radius on this platform?
Maybe a better question for Sonia, but what I can say is that at least as a user, there's a minimum bend radius parameter in the technology files that's distributed with the PDK. So as a designer, that's something you can just work with directly. You don't actually have to sort of work this out or anything. It's set by the foundry, and that gives you the confidence that it's going to be right.
Yeah.
But I imagine it's also wavelength specific. So
Yeah.
Mm-hmm. And what about the heaters? I guess the question is if they are present in the PDK.
They're not present in the current PDK, but I believe they're coming very soon in the runs that Sonia was talking about.
Yes, the runs that we are gonna do in October, they will have heaters. And yeah, the technology description is in the design manual that will be released early next week, but we have not yet implemented it in the PDK. So you can design with them, but they are not in the PDK. We should add that building block.
Yeah, but for just like for any of your designs, you can always feel free to contact our support. And if you need help with any building blocks, then we are happy to help you out. maybe one last question to make sure that we leave with a good message to our listeners. So when can our designers expect to be able to access this PDK?
Yes, I see a similar question in the chat. I believe at the moment the PDK will be distributed by Luceda. So anyone that's interested in using this, they can just contact us on our website and we'll get in contact with them and send it directly.
Indeed. Thanks, Matt. If there are no more questions, then I think we can thank the speakers again. So thank you, Sonia, Jonathan, and Matt for the nice presentations. And thank you, everybody in the audience, for asking questions and keeping the webinar alive. So thank you so much for your attention. Again, for any questions, feel free to contact info@lucedaphotonics.com, or you can also contact Sonia directly. And we hope to be in contact with you soon for your tape outs with Aluvia.
Thank you very much, Chiara, and thank you, Luceda, for organizing this nice webinar.
Yeah,
Thank you. Thank you.
Thank you. Bye.